All right. Hi, everyone. So we're going to continue our seminar series today. We're very happy to have Xuchen Cao
Yes.
from UIUC giving us a talk about one-sided black hole and DSSYK model and algebraic approach. Please.
Yes. Yeah. Okay. I mean, I'm just looking for a clock, so I can have a control of time. But yes, I mean, today I'm going to talk about one-sided black hole in double-scaled SYK model from an algebraic perspective. And this is a working collaboration with Pingao. And yeah. First, we start from a few explanation. Let me hide this bar. So I mean. Okay, let me hide this. Okay, I mean, let's explain first what is SYK model. SYK model is just a strongly interacting model with n flavors of Majorana fermions with this form of all-to-all interaction. And these G's are not fixed numbers. They are random numbers drawn from Gaussian ensemble with this kind of distribution. Here I just chose some kind of a normalization scheme here. And it won't be of much importance in the following. So I won't elaborate much on this, but okay. And on the other hand, we need to explain what is JT gravity, as we will talk about some of the relationships between SYK model and JT gravity. JT gravity is a 2D gravity model, which is topological in the bulk, and all the dynamics actually live on the boundary. And here we have the action of JT. I just wrote it down for fun. And in the following analysis, I think we will only focus on this term. These terms won't be really relevant, so I just won't discuss much about that. And we will come back to this term later. We will explain what this end of the word brain term means. And we can, I just say that we can impose asymptotic ADS boundary conditions on JT gravity. That's what we usually do, but not what we are doing here today. I mean, because here we are going to, today we are going to talk about the end of the word brain boundaries. But this is a Euro ADS boundary condition in JT gravity, where it just takes the induced matrix to be a diverging constant, and this the boundary dilaton, the dilaton field, which is, I mean, this is a dilaton field, which is a scalar, which is actually a Lagrange multiplier, takes also a fixed value on the boundary. I just want to point out that this asymptotic ADS boundary condition is basically you take the Dirichlet boundary condition for both the dilatons and the metric.
Sorry, G nu is induced on the end of the wall brains, and GUU is induced on the boundary. Is that what the notation is?
Yes, I mean, this is the notation I choose to use. I mean, U basically stands for asymptotic ADS boundary, and V is basically the induced coordinate on the end of the word brain boundary. But as you will see, this is not of much importance because we are not talking about GT gravity. We are mainly talking about the double-scaled SLK model, where there's actually not an induced.
Sure.
Yeah. SYK model, it has a dual to GT gravity. What do I mean by that? For example, you can just calculate the partition function of the SYK model in certain sectors. For example, in the low energy limit, and you will find that it's actually equivalent to a partition function of GT gravity. If you take the asymptotic ADS boundary, I mean, in the near ADS.
But we usually don't say that it's dual to it. It's just that the partition function at this matches the partition function. Well, actually, in the large n limit, the partition function with this match. Also, only for p equal 4.
Yes.
Okay, so
right, but I mean, here I say a duality because I'm going to talk about that construction by Henry Lin. I mean. And so yeah, and other people later, and which looks more like a duality because there is a correspondence at the level of Hilbert space and algebras.
Okay.
Yes, and that is why I say this here. But now, I mean, let's explain what is the double scaling limit. Well, I mean, usually we take this p to be just a number of order 1, like 4, p equals 4, or sometimes maybe p equals 6, etc. But here we take p to be a very large number, which in the large n limit scales with square root of n. Right? So it's large, but n small. I mean, it's of one its order is smaller than n, but it's still infinite. And we take this combination p squared over n to be a finite number in the larger limit, and this q is defined in this way. And again, these are just some kind of a normalization scheme for like coupling constants, which we won't care much about there. And the double scale limit allows for explicit solution of the model. And here by explicit solution, I mean just the explicit calculation of the partition function, which is just a sum over like this what we call the color diagrams. And all the details of this calculation can be found in this paper, Berkutz.
Can you explain it? So what is the number of fermions? The psi have some index, other index.
The number of fermions, you mean? Yeah.
What is n?
Oh, n is a number of Majorana fermions. I use a total number of Majorana fermions in the system, which is taken to be infinite. And I mean, this p is taken to be the number of fermions that gets involved in the interaction term. That is, you have a p-body interaction and you have an n fermion system.
So there is another index in the psi.
Can you say it again? Sorry.
In the Hamiltonian, you have another index for the psi.
Yes. You we have another index for psi. Yeah, I mean, yeah, it's an all-to-all interaction. You just randomly pick like.
Can you show the Hamiltonian again?
Yes, sure. Yeah, I mean, this is a Hamiltonian.
what's the-
Yeah, and you have psi's here. You just pick.
I go from 1 to n.
Yeah,
Yeah.
I's run from one.
Yeah, I from 1 to n, but they has to be different. I mean, because these are Majorana fermions. If there's
That's just a question. What's the curly J?
curly J is just some constant, like representing the scale of the like coupling, right?
What's the difference between that J and the usual J? In the
I mean, I'm just saying that, I mean, sometimes people use like different notations for this. I mean, these are just the difference of normalization, which won't dwell on, I mean, the remaining part of the talk. So far, so good?
Yeah, I do have a question. So if you looked at n choose p.
Yeah.
So over there, you normalize by n choose p, and here you're normalizing by p minus 1 factorial over n to the power of p minus 1.
Yes.
So for general p and n, where I'm not taking any scaling limits, what is the nice limit? Which one is the nice limit?
What do you mean by which one is a nice limit?
If I take n choose p and take p to be order 1,
Yes.
I seem to be getting this expression.
Yes.
So is the n choose p the right normalization?
N choose P, I mean, where did I show N choose P here?
When you're talked about p order in your double scale and choose p. Yeah.
Oh yeah, I see what you mean. It's just some kind of like well, there are I mean, I'm just repeating. I mean, the normalization which is used in this paper. I'm just saying that. I mean, in this paper, the authors like specifically choose this normalization scheme. And the point is that if we choose this normalization scheme, then we can there is some kind of a simplification in the when you calculate the like the partition function. I mean, via color diagrams.
Understand.
Yeah, I mean, yeah, it's actually some like just some notation, and
I think it's more than notation. It's the number of terms that contribute to the Hamiltonian, order of the number of terms that contribute to Hamiltonian. Because you want to put p size in there.
Yes.
And then there are n choose p choices to make.
Yes, right. Yeah, right. I mean, you are, yeah, I mean, you're right. I mean, we have to like pick this scaling of the coupling constant to make like the limit like well behaved.
Yeah.
And yeah, I mean, yeah, I see what you mean. And now, I mean, let's see how do you do the calculation for the partition function in double scale SYK. Here, I mean, if we are going to calculate the partition function, we are always going to like calculate this like I mean the moments, I mean of the trace of the moments of the Hamiltonian. And here the bracket just means the ensemble average. And remember that we are having a random like coupling drawn from some ensemble. And And it turns out that this can be calculated using the so-called color diagrams. I will use this example to show how color diagram works. Now let's see. Let's say you are trying to calculate this trace h to the 6, and then I mean you just draw all these like circles with like 6 points on the boundary, which we will just call 6 insertions. And you draw, all possible pairing patterns of these six insertions. And for like each diagram, you have you count the number of crossings. And this has 3, this has 1, this has 0. And for each crossing, there's a factor q. If you remember, q is just the e to the minus lambda, and it is a number smaller than 1. So this is q cubed, this is q, this is 1. And now, you just sum up all possible diagrams and to get the value for this, the trace of the h6. And in this way, you can calculate all possible moments of this h. And the explicit formula of trace e to the minus beta h is just by summing up the results for like each moment.
Can you go one slide back?
Yes.
So your q is e to minus lambda.
Yeah, lambda is.
So the lambda going to infinity limit basically picks up only the one with no crossings.
Yes, exactly. That's a great observation, and a lot of like derivations becomes much easier in that limit, and that is called the free limit.
Sure.
In that case, you just get a free probability theory. And now we can add matter. Matter operators can be added, and the correlators like well, the matter operator is just an operator of this form. Here, JA is just some random numbers from drawn from another Gaussian example, which takes the same form as the one like I have shown in the Hamiltonian. And this PA is a different number, but the PA is of the same order as P, which is again some kind of like well, you can define well, PA is of the same order as P. And then you can you can just calculate correlators like this. Well, you just insert a few like matter operators, and you insert like edge operators between them, and you can calculate this these correlation functions. And the way is that, for example, here, for each string like this, you just draw a diagram like this. Let's say, here you have a string h, h, m, h, h, m, h, m, h, m. And then, this diagram is calculating the function for, these two diagrams is calculating the correlator for this string. And then, you just draw like all possible like pairing up patterns like this. And you have the, and here notice that the matter can only be paired to matter, and the gravity cause can, I will explain why I call it gravity cause later, but the gravity cause can only be paired up with gravity. And now, we again count different kinds of like crossings. A factor R for gravity matter crossing like this one, and the factor S for matter crossing. Oh, sorry, there is a typo here. A factor S for this kind of.
Right. Did you need to introduce a second ensemble? What if you just wanted to calculate trace of, so let's say I'm not going to introduce JA.
Yes.
I'm just going to calculate trace of h to the power of k1 psi hk2 psi. We can do that calculation, right?
What is the psi?
Psi is a fermion.
Oh yeah.
Instead of picking particular m's with random ensemble with some random coefficients, why can't I just calculate just correlators of psi separated by?
That's a good question, but it turns out that these matter insertions behaves as if they are some kind of like heavy matter coupled to background geometry. JT gravity.
You made it a 2-matrix model. That's what I'm wondering. So you have 2 ensembles now.
Yes,
Right.
That's 2 ensembles. Yeah, you're absolutely right. This is somehow like similar to a 2-matrix model. And there are some constructions regarding these 2-matrix models to like mimic like matter moving on some kind of JT gravity background, right? By Kochmer,
Yeah.
Jeffers, and those people. I don't remember exactly who.
But you're going to tell us what is nice about random matter, about this.
Yeah,
Okay.
Yeah, this is what's nice about this. I mean, the reason I want to choose it to be random is that I somehow want to get something which is similar to a two matrix model. And the reason I'm taking this PA to be very large is that I want some kind of like heavy like matter moving on some kind of background, right?
Okay.
Yeah, I don't want too light matters, which.
Okay.
And now we can slice up. We now I mean here comes the important thing. We can like here I explain why we can view these chord diagrams as some kind of partition functions correspond as some version of the discrete path integral. I mean like for discrete like bulk geometry. I mean the yeah, I mean, once we can slice the diagram open and define a Hilbert space specified by chords. I mean, these lines are called chords. I mean, in the literature, on a slide. Now, I mean, you just take this chord diagram and you just slice it open in this way. Let's say, and now, I mean, on each slice, I mean, you have a finite number of chords, right? I mean, for example, on this slide you have 2. On this slide you have 4. On this slide you have again 4, and on this slide you have 2, right? And then there is a Hilbert space. I mean, you can define a Hilbert space which on each slide, which is specified by the number of chords, right? And now you have a state 2, you have a state 4, you have a state 4, and you have a state 2. I mean, on this slide, and I mean, this is how the bulk Hilbert space is defined, right? I mean, is there any question up to this point?
I have a question. So the P order 1 case, so JT.
Yes.
Sorry, regular SYK.
Yes.
That is in this picture, lambda going to
0.
Q going to 0, right?
Yeah. I mean,
It's not. It's Q going to 1.
Yeah, Q go to 1 limit. That's a
it's
JT
Q
graph.
equal to 1 limit.
Yes.
I see. So these are on this Hilbert space, the action of when you, you're gonna end up with some Q deformed commutators, commutation relations.
Yes, exactly.
Right?
I mean,
And the Q equal 1 is the standard bosonic commutators.
yes.
Is that
I
right?
mean, yeah, exactly. I mean,
the Q equals 0 is a free.
the free limit. I mean, the free limit, I will call it extremely like quantum, like extremely discrete limit. And but the free limit is nice for like doing some explicit constructions. For example, I will talk about the boundary algebra and its non-trivial commutant.
Sure.
And that non-trivial commutant was actually first constructed in the free case, because in that case I can use a series representation of some operators I want.
Sure.
I mean, question.
So the Hamiltonian that you showed in the previous one.
Yes.
The matter
No, it's not the Hamiltonian, it's a matter operator.
The matter operator.
Yeah.
So, well, like my question is like, should I think of the SYK Hamiltonian, like the dual of SYK being the pure GT gravity, which you were sort of in those diagrams you're calling the gravity chord, and the matter insertion as the like this one in the matter chord is the dual description.
What do you mean by a dual construction? Sorry.
So when you say gravity chord, I'm really confused. So you thinking about the dual picture and in the bottom?
Yeah. I mean, I'm saying that well, the gravity chord. I call them gravity chord because basically, I mean, you can in the picture I showed in the next slides, the number of these gravity chords can be understood as some kind of discrete length. I mean, of your geometry. That's why I call it a gravity chord. And it appears in the Hamiltonian, right? And is that your? I mean, I have to say that actually, I mean, just from its form, you cannot distinguish which is gravity and which is matter. I mean, yeah, I mean that's a very good question. What it turns out to be, well, I mean, they're actually treated on equal footing. I mean, in this double scaling limit. But the problem is that what really matters is that which one you choose to represent the geometry, right? I mean, for example, I just choose one of our chords as a gravitational chord, and how many chords I have, I mean, on a slide actually represents how long this slide is, which has a meaning of length there. And another difference is that when I take the GT gravity limit, I will take the number of this gravity chords to infinity. And by doing that, I'm restoring some kind of a continuous geometry there. Yeah, so that's where the asymmetry between these different kinds of codes comes from. But you're right. I mean, if we just consider the double scaling limit, then I mean they're actually equal.
This theory is somewhat topological.
Yeah, I mean it's actually topological. I mean,
It is topological.
yeah, I mean it's topological. Yeah, that's a point, right? Because the GT gravity is also topological because all the dynamics actually happens on the boundary, right? Yes. Well, now, I mean, despite this definition, I mean, now, I mean, since we have a Hilbert space, we want to ask, I mean, what is the inner product between different like states right there, right? So, I mean, actually, this kind of a diagram actually gives the explanation that you can, for this diagram, you can slide, you can choose a different slicing. I mean, you can slice it open in this way and into 3 different subregions. And you can say that, well, I mean, this upper subregion prepares a state with 3 chords here, and this lower subregion prepares a state with 3 chords here, and they just, I mean, and the inner product is calculated by this region. I mean, so basically, the inner product is basically just but done by counting the crossings, right? The relevant Hilbert space in this case is a Q-Fock space. A general state looks like a string in that. I mean, because generally speaking, you can have like both gravitational and matter chords. So I mean, so you should label the state with a string like this. Like for example, this state is just the gravity, matter, gravity, something like that, and a state like this. Now, I mean, the inner product between 2 different states can be calculated by these diagrams. You just like put 1 state here and 1 state here, and you consider all possible pairing patterns, I mean, between them like this. And again, I mean, we follow the rule that gravity can only be coupled to gravity, paired up with gravity, and the matter has to be paired up with matter. And you sum over all possible pairing patterns, and for each pairing pattern, you have like a factor, I mean, corresponding to these crossings, I mean, which is the same as the pattern I introduced before, like gravity called crossing as a factor Q, etc. And you just sum up all possible like definitions of the all possible crossings, and you just sum up all possible like crossings to get the inner product. I mean, although this inner product is constructed in a very complicated way, but it turns out it's indeed a well-defined inner product. It's a positive definite, and yeah, I mean, it's positive definite, and it satisfies all the like different like definitions of the inner product.
So you're calling this a Q-Fock space. I understand why you say that, but it's basically 2 Q-deformed. Well, yeah, for pure gravity example, it would be a single Q-deformed harmonic oscillator.
Yes.
And for the example that you have with two matrices, it would be 2 sets of Q-deformed oscillators, A and B.
Yes, and they have their Q commutation relation is generally characterized by a matrix, right? It's like QRS, something like that. Yeah, I mean, but there's a whole bunch of mathematical literature studying this structure, and they proved like everything like this, like the boundedness of Q oscillator operators and the well-definedness of the inner product here, something like that, and by a bunch of people. Bojeco, Speicher, and yeah, if you are interested, I can provide you all the like literatures on this later. Now, I mean, we can define the code Hilbert space helps calculating the traces, and to do this, we first introduce the code creation and annihilation operators. The code creation operator, I mean, I have to say that I have these indices R because I'm just defining all these operators to act on a string from the right. For example, this creation operator just creates a new like chord on the right, and this annihilation operator just annihilates an arbitrary operator. I mean, from the block. I mean, their action actually looks like this. I mean, this is a creation operator, and the creation operator just creates a chord on the right, and the annihilation operator just annihilates. I mean, an arbitrary one of the existing chord. I mean, from the existing state. Here I'm showing the case that it's annihilating this state. But when you remember that when you act with the annihilation operator on the right, you actually get a linear combination. I mean, because it can annihilate all possible codes. It annihilates, for example, this code, this code, this code, and you have to add up all the contributions. And also notice that when you annihilate the code, you inevitably like create these like crossings, right? Because if you want to annihilate this code, you have to cross all the codes to its right, and so I mean this contribution, I mean this term contributes a factor like a q squared. And if you are like annihilating this code, then you are it comes with a factor q to the fourth.
Sorry, can you go back?
Yes.
I just let me ask my question again. I'm perplexed by the index I. I thought there would be no index I for any dagger. So what's the range of index I? What does it run?
It's in this case it's 0 and 1. I mean 0 just means gravitational code, and 1 means
okay, so
matter code.
this is just colors. Eyes run from black and blue.
Yeah, black and blue, and that's just the colors, and it's just well, because the gravitational gravitational creation operator can only create a gravitational code, and the gravitational annihilation operator can only annihilate a gravitational code, and yeah.
So the label of I runs over your matrix number of matrices.
Yes. You can of course you can have an arbitrary number of like matter operators, and that's but that makes no significant difference. So I will just stick to the case where you have two different kinds of codes, and you can show that. I mean, very astonishingly. I mean, with respect to the inner product we defined in the last page, these two operators actually they are conjugates to each other. I mean, this is a very amazing mathematical conclusion that here we have. I will just emphasize again that we have defined the operators to act on the right, but you can equally like define operators to act on the left. And that's a little bit like the left and right algebra in JT gravity, boundary algebra in JT gravity. And I will just talk about their relationship later. Now the boundary Hamiltonian and matter operators. Now, I mean, I define this boundary Hamiltonian and boundary matter operator in this way. Like, well, it's just a linear. It's just the sum of creation and annihilation operators. So it either like creates or annihilates a code. Now, I mean, it can be proved that well, let's define this omega to be the vacuum state with no codes. I mean, no codes leaving on slide. Now, I mean, you can show that. I mean, when you are calculating this trace, it's actually calculating this amplitude, the vacuum to vacuum amplitude of the right Hamiltonian, and raised to the same power. And you can replace this with the left Hamiltonian. I mean, of course, and yeah, and the conclusion also holds. And all operations can be also, yeah, I mean, yeah.
You're just doing you would build the operator algebras from the GNS quantization. Basically,
yeah.
You take your vacuum, act with HR, and you get chords, and they span your Hilbert space. Yeah.
Yeah, exactly. That's a GNS construction. Yeah, there's a whole bunch of proof of like cyclicity, like yeah, I mean, like cyclicity and separability of the states. I mean, in the GNS construction, something like that. And, yeah, and this. By the way, I have to say that in this case, if you use the GNS construction, you can actually restore the whole like Q fork space.
Yeah,
you can just because you can build an arbitrary word. You can build an arbitrary like word out of like A0 and A1. I have to say that this can be like from the paper by Berkut and discussed before. You can show that these Hamiltonians can actually be diagonalized in this way. These Hns are functions called the Q-Hermit polynomials, which is defined by these recursion relations, and the E is actually bounded. The theta goes from 0 to pi.
So I have a naive question. So this whole theory you're describing is a deformation of simple harmonic oscillator.
Yeah, I mean, this is a whole I mean, in this case, it's a deformation of the simple harmonic oscillator because here I'm just talking about the one cause.
So the deformation of the Heisenberg algebra of A and A dagger, right?
Yeah.
Now, gravitational theory. Once you think, I know that you didn't want to consider boundaries, but the theory had SL2R to start with.
Yes.
The SL2R was acting on trivial and the boundaries, and you're completely ignoring that. But is the idea that once there is a way of embedding this in the story that makes it a QT-form SL2R?
Yes, there is one. I think there is this interesting paper by Stanford and Henry Lin, which talked about a analog of the SL2R algebra. I mean, in this model, right? And
But the Hamiltonian de Hamilton oscillator would be A dagger A.
Yeah.
A plus A dagger is just like X.
Yeah.
So here the Hamiltonian is X.
Yeah, but the algebra that they're working with, it's just NA dagger. Except, so the algebra is Heisenberg algebra, commutative of X and P I. That's the algebra, and then they're forming it. But if you have PSL2R, you'll have L0, L1, and L minus 1. That's they're related through exponentiation.
Yeah.
There's this, I wonder if that would provide an angle to understand this, but anyway.
yes, yeah. I'm actually not talking about this aspect in my current paper, but this is indeed like discussed. I mean, in that paper by Lin and Stanford. I mean, because they constructed like the from a chord perspective, from this annihilation and the creation operators. I mean, the generators of three operators, which looks like the generators of the SL2R. I mean,
There's another thing I want to say. Well, of course, if you have ANA dagger, you could construct PSL2R by looking at A squared minus A dagger squared. There's this combination.
But what's the commutator of A and A dagger here?
yeah, I mean, well, yeah, I mean, there's the commutator of A and A dagger. Actually, a Q commutator of A and A dagger here. You just replace.
It's A dagger minus Q A dagger A is 1.
Oh,
Yeah, I mean, there is a Q commutator here.
That's the Q combo.
Yeah, it's just a replace. Yeah, you just add a Q. I mean,
But I also just a comment. I know that you're not discussing that, but Henry Lin, Stanford, or other people, if you were to describe the following object, a generating functional for time evolved correlators of psi or average size, as we do in SYK usually,
yes,
as a function of time,
yes.
then that would be a QT form PSL2R. Is that what the idea is? Or PSL2R, yeah.
No, I don't think they are talking about the correlation functions of psi, right?
You could talk about it. I thought that was what we were. Okay, well, let's talk about this.
I mean, we can talk about more details later,
Yeah,
but
sure.
yeah.
Slides.
Yes.
What's the for the recursion relation? What is we have H0, but we need 2 times, right?
We have. Oh yeah, I mean here actually it's just the H0. I mean.
I mean the last equation you have Hn to Hn plus 1 plus Hn minus 1. But
Yeah, I mean right. I mean here I mean maybe I'm missing one here, but you can say something like H minus 1 is a 0 or 1. I don't remember, but it's a constant anyway. And now we are talking about this what is the so-called triple scaling limit in the literature, which is actually just the continuum limit. Now we take lambda goes to 0 and q goes to 1. That's a limit we discussed just now. And but we take n to be very large, such that this lambda n goes to infinity, and we take this renormalized length to be a constant. And this renormalized length basically looks like the renormalized length in JT gravity. And in this case, SYK model somehow reduces to the case with finite p, and which is known to be dual to dual to GT gravity. I mean, in the sense I discussed it before. I mean, in the sense of the partition function. And the Hamiltonian reduces to a Liouville Hamiltonian. In this case, you can just take the Hamiltonian of the discrete takes the continuum limit of the discrete Hamiltonian I just described before, and you can show that that reduces to a Liouville Hamiltonian, which is a Hamiltonian for 2 boundary JT gravity. I mean, the Liouville Hamiltonian looks like this. The JT partition function is just the Euclidean vacuum to vacuum amplitude of the Liouville Hamiltonian. I mean, you can just interpret the JT gravity partition function in that way.
So sorry, just to understand the limit. So this is when lambda is 0, q is equal to 1. So you have the undeformed theory.
Yes, somehow, yeah. I mean,
so you take it double scaled, but then focus on small deformations.
Yes.
Within double scaled, and then you you find the JT Hamiltonian. This is the JT Hamiltonian.
Yeah, I mean, this is a JT Hamiltonian. Yeah, found by Jeffers and yeah, and Daniel Hartwell. Yeah, there's an earlier paper. Now I will say a few words about boundary algebras. I mean, the boundary algebras is defined for can be defined for both GT gravity and double scale SYK model. I mean, the two-sided double scale SYK model. And now you can imagine that the GT gravity looks two-bounded GT gravity. I mean, in Lorentzian signature looks like this. And you can define like operators acting on the left-hand side and on the right-hand side, and there is a description of the bulk Hilbert space. And now, I mean, the algebra on the left-hand side is generated by the left Hamiltonian along with all possible left matter fields, which I collectively write as psi, and so does the right algebra. And there are a few papers like proving that both these algebras are of type 2 infinity.
So I'm still perplexed, but can you go back one slide? So what is the theory? So your starting point, so your endpoint is JT Hamiltonian. Your starting point was a theory with both random matter and average J, or do you need random matter?
Oh no, I'm not coupling to random matter here. I'm just
pure graph.
Yeah, I'm talking about the simple case that I have just one like code, one type of code that is pure gravity, and yeah, I have to say that if you consider like random matter and like take this limit, things become very complicated, and I don't have a very nice like theory for that. That is will be included in my following works, but
right. The thing that is really interesting is that your theory of without matter, right, is a topological theory.
Yes.
For the Q deformed version.
Yes.
You take a particular limit of
Yeah.
that Q deformed version.
Yes.
And you end up with some Hamiltonian quantum mechanics, which actually has dynamical degrees of freedom. It has PSL2R and it's non-topological.
Yeah, but it's on the
It lives on the boundary, but still non-topological. There's a PSL2R action.
Yes.
It's kind of magic.
Yeah, I mean that's a very good question. I have to think more about that, but we can discuss that later. Yeah, okay. That's a very good question on that. And now we can also define the boundary algebra. I mean, in the two-sided case, I mean, now, I mean, in this case, I'm going to incorporate matter because, I mean, if I don't incorporate matter, it's just the algebra generated by a single like entry. So it will be just a trivial, it's just an abelian algebra. And now, I mean, I define, I consider the case where I have both gravity and matter. Now I define the left algebra to be the one generated by Hamiltonian and matter operators, I mean, acting on the left, and the right algebra to be that generated by the ones acting on the right. And again, I mean, it can be proved that these two algebras are actually type 2-1 like factors, von Neumann factors. The difference between, yeah, I will explain here. I mean, a von Neumann algebra, I mean, is just a sub-algebra of BH closed on the weak operator topology, and A is called a factor if there's no non-unit operator in A which commutes with everything in A. And it could be classified into one of these three types. And I mean, a factor could be classified into one of these three types. And today we are going to talk about the type 2 ones. The type 2 the factor does not have its own subspace to act on, but nevertheless, we can define traces on it. And if the trace of the unit element is finite, we have the type 2 one. And if it's infinite, we have a type 2 infinity. So we will focus on the type 2-1 case here. Now in the JT case, I mean, it's type 2 infinity, and we can prove that the AL is actually the commutant of AR. I mean, the commutant just means everything bounded operator which commutes with some algebra. So AL is just everything which commutes with AR. And by doing this, by showing this, we can show that if you put AL and AR together, you can generate everything in BH.
So sorry, these statements are correct if your boundaries sit at some finite, you've regulated, right? You've regulated your disks.
Yes.
Right, so by introducing a boundary, and then this is what you have to.
Yeah, I mean, this is, I mean, in the JT case, you need a regulator on the boundary.
Sure.
Because we are talking about yeah. And but in the double scale SYK case, there's no regulator to be defined. And in the double scale SYK case, I mean, these two are both type 2-1 factors. and they are again like commutant of each other.
How do you see their type 2-1? How do you show that?
I mean, this is a, well, there is a naive like argument. I mean, because I mean, these were like shown in explicitly in mathematical literature before, but I will just say a naive like argument, which is like you can show that the vacuum state omega I defined just now is actually a trivial state on that.
So is this statement that the Q-deform harmonic oscillator algebra is 2-1?
Yes, I mean there is a conclusion like that.
So that's generically the case that if you constructed genus from the action of A and A dagger that are Q-deform, you get type 2-1.
No, it's actually you do the GNS construction for H and for H0 and H1, not for A and A naught.
But those guys are the algebra they generate is just A and A daggers, right? Q-deform A and A daggers.
No, if you include all the A and A daggers, I mean, for example, on the right boundary, then you can generate everything. You can generate the whole algebra on the, I mean, in the bulk, not just the
So
type.
what is the algebra that's type 2-1? I'm confused.
Oh yeah, it's algebra generated by HR by this. I mean HR naught and HR1. Sorry.
Well, let's just take HR0. Let's just take that one alone.
Yeah.
Is it true that von Neumann algebra generated by that guy
Yes.
on the TFT state or vacuum, whatever you want to call it, is type 2-1?
No, that is not a factor, right? I mean, if you just take one, if you just take one of these operators and generate algebra, it's actually a abelian algebra, right?
Sorry, Q-deformed or not? Q-deformed, it won't be abelian.
No, I mean, if you just take one operator, let's say HR naught.
Yeah.
And then you generate an algebra, I mean, using that HR naught, then, I mean, for example, all the polynomials, they, I mean, commute with each other. So it's not a factor.
What is value of Q? What is lambda now? Well, have you set Q equal 1 or not?
No, it does not depend on Q equals to 1, right?
You just have one element of the algebra.
But it won't be, no, it won't be.
Basically, all your elements, either identity, HR, HR square, HR cube, all the things are commuting, no matter how you define your computation.
Depends what is the theory we're discussing.
Oh,
Depends what you mean by HR. If you mean by HR, the things that are these, yeah. Of course, if you tell me HR, if you're telling me you're discussing just JT or just, yeah, then I agree with you. But anyway, why don't we continue? I think this is a distraction.
Yeah, I mean, yeah, I mean, I just want to say that if you have an arbitrary algebra and you just take an arbitrary element and you consider everything generated by that element, of course, it's a bounded operator, then you have an abelian algebra, right? Which is equivalent to the algebra for like continuous functions on the spectrum of that operator, right? Yeah. Sure. Now let's talk about the end of the world brain cases. I mean, well, just don't be distracted by this apocalyptic name. Sorry, I always have some problem pronouncing that word. I mean, but just don't be distracted by that. It's just a Neumann boundary condition. It's really just a Neumann boundary condition for like both the metric and the Dirac field. We just fix the derivative that is actually the extrinsic curvature of the metric on the boundary, and we just fix the derivative, the normal derivative of the Dirac field also on the boundary. And this is called the end of the world brane. And if you remember, I mean, what we said about the boundary term for end of the world branes, you will find that there, in the presence of this end of the world branes, you have an extra contribution. I mean, to your action from the UW boundaries, which takes this form. This mu r is a constant. This mu r is a constant called the tension of the brane. And this ds is just the integration over the length, the invariant length of that boundary. So I mean, it's just the mu r times length. And
so they're sitting in geodesics.
Yeah, it's geodesic.
That's why you said Q equals 0.
Yeah, that's a good point.
And that's dynamically fixed in the bulk.
Yeah, it's a dynamical object. This is very different from the asymptotic ADS boundary condition. Yeah, I mean, that's actually the key difference. And the features of end of the world brains, I mean, it's a boundary with non-trivial length, and it's actually a geodesic and contributing a factor e to the minus mu RL. I mean, when calculating partition functions, right? And in double scale SYK length, it's just the number of gravitational chords. And this actually indicates what we should, how we could define end of the world brains in double scale SYK. Therefore, we define the end of the world brains in double scale SYK as an object on which chords could end. Because whatever you have an object on which a chord could end, then you just have then that object has a non-trivial length in double scale SYK, right? Because I mean, I have discussed it before that the number of chords is basically just the length, the discrete length of something. I mean, in the double scale SYK. So
we're gonna get, so we start with, I think that's the answer.
yeah, I mean, this is
So we started with topological theory with closed boundaries. Now you're gonna introduce open boundaries.
it's not really an open boundary. It's a dynamical boundary, I would say.
Yeah, it's open boundaries because your boundary is now an interval, right? And it's
No.
extended into both by
Oh yeah,
shell.
yeah. You are saying that it's
So the diagrams you were drawing,
yes.
yeah, I think. Well, you're looking at disk partition function, so that's all that there is. These pictures are all. Well, no, you could have a bunch of end of the world brains like this. Take the disk and take a bunch of bytes from the corners of it.
Yeah, I mean, of course.
This is an open. That's a disk contribution to open TQFT.
Yes, right. I mean, in this sense, I think you're right. But I'm just oh yeah, I think by closed, I'm saying that they are closed because in the following like discussion, I want to let like matter like leak from this boundary. So that's why I say it's closed here. Okay, but I think in your sense, you're right. I mean, you can say.
And introducing, of course, when your boundary was topological closed boundaries, your algebra is Abelian. But now once you introduce open boundaries, that opens up room for non-Abelian algebra.
No, it's actually no. I mean, even in the case above, I also have a non-Abelian algebra because I have added those like matter operators on the boundary, right? The matter operator actually
But
doesn't.
even without matter, I think if you open boundaries, you're gonna get non-Abelian.
It's actually again Abelian. I mean, as I will show, because
Okay.
there is a single like Hamiltonian operator on the boundary, and you can just generate like. Well, I'm not letting things. I mean, because I mean here I'm considering the algebra from this side because I mean this model, by using this model I'm trying to mimic a one-sided black hole. I mean, on the end of the world brain. So what we will usually be interested in is the bulk reconstruction from this side, right?
Sure.
Yeah. And we can sum over like well, we just sum up like all chord diagrams, which looks like this. I mean, where we have an end of the world brain on the left, and our chord diagrams can a chord can end on that diagram. So it looks like this. And now, I mean, we introduce a parameter which is called the brain tension. Mu is smaller than 1. And for each end of the world brain chord ending on this end of the world brain, we bring a factor. We like multiply the diagram by a factor mu. For example, this has a mu square, a mu cubed, something like that. And we just and we can again do a similar like slicing of this diagram into this.
So sorry, what is the length associated to an end of the world brain? Is it the number of chords that end on it?
Yes,
That's the expectation. That's in this Hilbert space, is L an operator? And are these the eigenkets of it? Are these the eigenvalues of it?
What L you mean the L ending on this?
So length in classical geometry is classical object, right? You give me a path, I give you a length.
Yes.
Here, length, the values that you associate to them are discrete.
Yes.
So it's just positive integers.
Yes.
Okay, we'll see.
Yeah, I mean, we will see, but we're yeah, I mean, you can. I will reach this point later, but you can indeed define some state like corresponding to this you can define a state like on this and which we will use later, and you can do this slicing, And again, you can do you can also slice the diagram in this way to define the inner product, and which it turns out that actually the inner product is the same as the inner product defined for the two-sided case before, but it's just what has changed is the rule that how these insertions prepare a state. I mean, on these slices. For example, I mean, if you don't have this end of the word brain, then the state preparation rule is different. You can't have a like a chord starting from here but ends on the end of the word brain. Now, I mean, if you just stretch the slice the diagrams before, you can say that now, I mean, with the Hamiltonian insertion on the boundary, I can either create a excitation or I mean analytic excitation. But there's one more thing I can do now. I can just shoot a end of the word brain chord from the boundary to the end of the word brain, and this term this won't change the number of chords. I mean, in that state, but it will multiply the state by a constant, which is q to the fifth. I mean, in this case, so it's actually some kind of like the number counting operator. I mean, in the bulk. So we conclude that. Now, I mean, the Hamiltonian, the H tilde, here I just wrote bulk, I mean, to emphasize it acts on the bulk here of space, but I won't keep this index in the following. But it's just the A plus A dagger plus mu to the QN. I mean, here A is actually on the right. I'm just dropping those indices. And mu Q to the N is just this N is just the number of chords, I mean, in the box state. And generally speaking, I mean, if you also have matter chords, then you have to add another factor R to the N matter. I mean, but that makes no big difference. And you can show that, I mean, the sum of all one-sided chord diagrams can be evaluated in this way. You start from the vacuum state, and you insert this operator raised to the power n, and you just project it to another vacuum state. This calculates this vacuum to vacuum amplitude of this new Hamiltonian. Actually calculates the sum of all like one-sided chord diagrams.
So these A and A daggers are Q deformed or not?
They're all Q deformed.
Okay.
They're just the same operators I mean defined before in the two-sided case. I mean, again, some diagonalization, which is complicated. I won't elaborate much on this, but you just I mean, these functions are called BQ continuous Hermitian polynomials, and I have to point out that the idea of using this orthogonal polynomials to study end of the word brains was first proposed by this guy Okuyama Kazumi from a different perspective, and you can see this paper for more details. But they just what they did is they said that there's a class, there's this family of deformation of the big Q of the Q continuous of the Q Hermitian polynomials, and they claim that by taking like continuum limit, that looks a little bit like end of the word brains. The triple scaling limit is a bit like different in this case, but it's basically the same. And you can just show that by taking the triple scaling limit. I mean, this is an argument by Kazumi Okuyama. I discussed it just now. And you can just restore like this kind of like a Hamiltonian. And this Hamiltonian is called the Morse potential. And it has been shown that in an earlier paper by my collaborator Pin with Kochmeyer and Jeffries, they show that there is this is actually the correct Hamiltonian, which captures the dynamics of a one-sided JT gravity model with one asymptotic ADS boundary and one like end of the word brain boundary.
So the extra term, the new term is just mu r e2 minus l.
Yeah,
so
I mean, this is a new term.
That's the only piece that you need to add.
Yes, that's the only piece I need to add. It's actually very simple. I mean, this can also be seen from the form of the from the deformed Hamiltonian I defined before, right? You are just adding an operator which counts roughly the length of the box state, which is basically this one, right?
So L is just a number.
Yeah, L is a number. I mean, it's actually an operator. I mean, it's actually an operator. It's actually just
confused about, because that's what I'm confused about. I would expect it to be an operator.
Yes.
But then you have that definition, the line above it.
Yes.
That confuses me. That's a number, right?
I mean, this is actually a very good question because I mean, what happens is that if you just well, I mean, because I mean, the continuum Hilbert space actually has a very different structure from the discrete one, right?
Of course.
Yeah, I mean, then I mean,
You're not, sorry, you're never in the. Oh, you're calling the triple limit continuous, okay.
Yeah.
I see, okay, got it, yeah.
yeah, so it's
So that the definition above is the definition coming from the, sorry, L B is what?
L of B is yeah, I'm sorry, I think I missed one of the equations here. I mean, LB is basically just like something like n times lambda. I mean, which is taken to be infinity. I mean, in the two-sided case. Yeah, you can think of it as you can think of this L as a renormalized length.
Yeah, that's what I'm wondering. So what I'm wondering is that initially you had this operator that had integer eigenvalues.
Yes, right.
Of course, if you just naively, and that is true for any cube.
Yes.
If you naively take, you know, like small q limit or q going to one limit, that's still going to be integer values, but you have to rescale it. So this capital L is a rescaled one.
Yes, I mean, it's a
supposed to be a
rescale.
differential operator.
Yeah.
Okay.
Yeah, right. Well, I can talk more about the details of this limit, but yeah, but I just want to highlight this conclusion that it indeed approaches the continuum limit, I mean, the correct continuum limit in JT gravity. Okay. Now, I mean, let's say, I mean, here comes the key. I mean, the Q coherent state, which is obtained by an alternative slicing of the diagrams. We can define this state, which is called the Q coherent state, with this property. And you can verify that this state is actually a normalizable one. You can calculate it's like norm, it's finite, and it satisfies this property. And you can show that instead of like doing the calculation using the H tilde, we can just use the on tilde like HR naught, which is just the A plus A dagger. I mean on the right. And you just but we instead of evaluating the vacuum to vacuum like amplitude, we start from vacuum and project it to this state. And there's
the statement is that equation is equal to what?
It's equal to the sum of all like one-sided chord diagrams, which is also equivalent to this.
Oh, so the statement is that. Oh wow, good. You're saying that your interpretation is that the vacuum expectation value in this deformed Hamiltonian is the overlap of the old Hamiltonian within acting on vacuum on the left. That coherent state represents the end of the world, right? So
yeah, exactly. That's a very interesting correspondence. Actually, Okayama Katsumi had referred to this course, had like discussed this correspondence in his original paper, but we just found many interesting ways to use this conclusion. I mean, to do a lot of interesting things, especially for algebras. But this is actually, yeah.
That's similar to the boundary state for Liebering.
Boundary state for what?
Liebering.
Yeah, I mean, I'm actually, well, I'm actually not very familiar with the boundary state for D-brace, but I think, yeah, we can discuss that later.
You have the like 90 degrees and you say the end. So sitting the ends on a given, you can describe this as the state of the closed string, or you can define as the loop of the open string.
That's like open close.
Right. I mean, yeah, because I mean, this can actually be found from the fact that you can just rotate these one chord diagrams by 90 degrees.
Yeah, that is.
Yeah, you can just view it from this perspective that you can start from somewhere here and do the time evolution from right to the left. And then you define a state, which is
open close valve. Okay, so it's just changing picking a different quantization frame.
Yeah, I mean, it's, I mean, another way of saying this is equivalently, you can just do this kind of slice. You can just treat these red lines as time slices, and it starts from vacuum and this ends on this end of the water.
Like defect versus charge. That's what it is.
Yeah, exactly. And if you stretch it, you just get this.
Yeah.
That's a very interesting viewpoint. And now, I mean, let's add matter to the one-sided double-scatter SYK. And now I don't want the matter to leak because I want my system to be closed. I don't want the end of the world brain to be coupled to some kind of external source. So I don't want my matter to like leak or being created from the boundary. So I would say that, I mean, I would expect that when I would take this reflective boundary condition, where, I mean, once the matter code just reaches the end of the world brain boundary, it's just to get reflected back, and which just looks like this. And nothing happens. So with this minimal like assumption, I'm just saying that this end of the world brain does not talk to the matter code at all. It only talks to the gravitational code. So so my conclusion is that the matter operator does not change in this case, and the only thing that changes is the gravitation. Is a gravitational operator, which as I said before, it's you just add it to it a operator which is mu to the qn, right?
Can the matter core end on end of the world brain?
No. Yeah, because intuitively, if a matter core could end on the end of the world brain, you're essentially saying that I could like annihilate. I mean, some matter particle is leaking out of that end of the world brain, right? That's not the case.
Yeah, but why is that bad?
Yeah, I mean, because I want this system to have well, because I mean, basically, I just want to put the reflective boundary condition, I mean, on the end of the world brain, because I don't want the matter to be like leaked from the end of the world brain, right? For example, you're considering a evaporating black hole, and then I mean, I just want, and then I mean, the radiation comes out, and I can collect it at the like at the asymptotic boundary, and I put it in another like, and I put it into some kind of a subsystem which is called the Hawking radiation, but I don't want like radiation to also escape from the end of the world brain, right? I think that's a motivation I'm trying to do. Yeah, because I'm trying to, well, my ultimate goal is to like mimic some kind of evaporating black hole, I mean, in this picture, but of course, I mean, in this paper, we haven't reached that far, and a lot of things has to be worked out in future, but in this paper, we just...
So in the sense of Pennington, Stanford, kind of...
Yeah.
Okay.
It's just a toy model for evaporating black holes, so that's why I don't want the leak from the end of the world brain.
Yeah.
No, I mean, in this case, I mean, here my H2 R naught is just the H R naught plus this operator. I mean, because here in the presence of matter, I have to add this factor as well. This N naught, and this H2.1 is just is same as untitled H2.1. And the right algebra is defined by the full normal algebra generated by these two like operators, which is the same as the two-sided case, except that I have an extra operator here. Of course, this immediately generates to the case with more types of matter codes that you can have HR2, HR3, and add them all into this algebra. But it does not make an essential like difference. Now, I mean, since we only have one boundary in this case, it's very natural to ask the following question: can we reconstruct all the block from this AR? This AR2, sorry, this is block. Okay, yeah, I mean AR2 that, and now I mean that is equivalent to ask whether we have AR2 is equal to BH. In the two-sided case, we know it's not BH because it has a non-trivial commutant which is AL. And now, I mean, it has now I will show that even in the case that you have a non-trivial, you have just one boundary, it's still not possible to reconstruct all the block from this AR2. Why? Because we have identified this operator. If you just substitute this operator, I mean, into the you can verify that it commutes with all the generators of the right boundary algebra. And you might ask that why there are still left operators, despite that we just have one right boundary, but no left boundary, no left asymptotic boundary. Because the answer is that despite the fact that we don't have a left asymptotic boundary here, but these operators are still legitimate bounded operators on the Hilbert space. So we can we can still construct that operator. Because here the reason I'm constructing this operator is just to show that the AR is not BH.
So what is the definition of A left 0?
A left 0 is just the annihilation of it's just the creation and annihilation operators on the for like gravitational chords from the left.
Okay, but why does that act on the Hilbert space that you constructed? on the
No, I
right?
mean, because the reason is that I'm just trying to show that this AR tilde is not BH. And by doing so, it suffices to just construct a legitimate bounded operator acting on BH, which commutes with that algebra, right?
Oh, okay. got it.
So this operator actually does the job.
Sure, yeah.
Yeah. So that's
But,
why.
right, I mean, it was.
Oh.
Didn't you say that AR tilde A tilde R is type 2-1?
A tilde R, yeah, I'm claiming that, but not from the, but I'm claiming that not because of this argument, because I'm
Sure,
going to
but like the moment you say that, it means that this cannot AR tilde cannot be B of H for sure.
Oh,
We'll
no.
have it,
What I was saying is that the AR without tilde is type 2.
but the only way for AR tilde to be B of H is that it's type 1.
Yes.
Probably, yeah. So this,
No, it's no. There's something subtle here. Showing that it's even if you can show that it's type 1, I think it does not actually tell you that it's actually like the whole BH, right?
yes,
Because
if
it's
B of H, it must be type 1.
yeah, if it's B of H, it might be of type 1. But I will give a separate argument why it's still type 2. Later.
Yeah, sure.
But yeah. No, I will just make a slight detour here to show.
By the way, time-wise, is how much more time do you need?
I think I can finish maybe in like 5 or 10 minutes.
5 minutes?
Yeah,
Okay,
yeah.
thank you.
I will just drop the last part,
Okay,
and
that's fine.
yeah, because it's not really relevant to this discussion.
Okay.
I will just speed up. We might ask what is the minimal the modification we need to do to the algebra to construct the whole block. This is a slight detour from what we are discussing just now, and very astonishingly, it can be shown that if you just include this operator, this number counting operator as an independent entry in your algebra, you actually can restore all of BH. The basic logic is that well, from this operator, you can by taking all possible limits. In the von Neumann algebra, you can construct all projections, all spectral projections. In this case, the spectral projections, are just the projections to subspaces with different values for n0 plus n1. And with these projections, you can just separate A and A dagger in this operators, in this H and operators, and then you can show that with all A and A daggers acting on one side, you can reconstruct everything in BH. This actually generalizes to the case with more types of matter chords. That is, no matter how many kinds of matter you have, by just adding this kind of operator, you can this generalized wormhole length operator, you can generate everything in the block. Now, let's give an argument on what's the relation between A tilde and the AR. Now, we just use this spectral decomposition of this vacuum state omega and this coherent state B mu. This theta states as I defined before, they're just those states defined by the the Q-Hermit polynomials. And then, you can show that. But by looking at the forms of the decomposition of these two states, you can show that I can define this this operator, and here the theta x is just this operator, and by construction, this BR0 is the element of AR, and onto that AR. And you can show that this function actually has nice properties. It's a continuous and it's bounded. So
sorry, is that the Q deform Poisson, or maybe another way of saying that is that the Pasteur-Marchenko distribution?
Which one are you referring to?
This BR mu.
That's a
Q
good question.
deform, so coherent state has a Poisson distribution associated with it.
Yes.
The Q deform Poisson is the Pasteur-Marchenko distribution. That's what it is. We could talk about this later.
Yeah, I mean, we can talk about, I mean, that's an interesting question. Actually, I want to, yeah, talk about those person like story you
Okay.
like wrote. Now it can be shown that the spectrum of HR not actually lies within this. I mean, these are shown in some mathematical literature, but by spectral mapping theorem, you can show that by just examining the properties of this function, you can show that this should be the spectrum of B. Sorry, I mean, I just made a typo here. The spectrum of B is strictly bounded by it's lower bounded by strict positive number, and it's also upper bounded. So you can define like these operators like its square root and its inverse. And more importantly, you can verify like this you can verify these relations. Note that, I mean, here I can move the BR like square root from the right to the left, because I mean this omega is the crucial state for the algebra generated by HRs, and as I said before, that this B operator is actually also in that algebra, so it's also crucial. And there, this state B square root B state. Now, I mean, we can consider like the span of this set and the span of this set, and I was able to show that both these two sets are actually both dense in the Hilbert space. And now we can define a linear bijective mapping, which is defined in this way. And it can be shown that it's linear, it's bijective, and it's also an isometry. I mean, by how I show it that it is an isometry is basically by just using, I mean, these relations. So it's actually a unitary from a dense subspace of the Hilbert space to another dense subspace of the Hilbert space, and by linear extension theorem, by bounded extension theorem, it can be shown that it can be extended to a unitary operator, I mean, on H. So, I mean, in this case, you can show that there is there's this unitary V which relates A theta and A, I mean, this way. I mean, because it relates all polynomials in H theta and H, and since it's a unitary equivalence, so it's preserved like undertaking the weak limit. So it actually interpolates this algebra to that one. And based on this, we claim that the AR theta is also type 1. It's also type 2. And I will just stop here. And there is another like interesting story about like the trumpet amplitudes and their divergence, but they are not very relevant to what I'm talking about today. So we can, if you are interested in that, we can talk about that later. And we have an upcoming paper which is going to be published maybe in 1 or 2 weeks, and which includes a lot more than what I discussed here, like the discussion, the relation to the GT limit, the continuum limit, and I mean, well, I mean all kinds of stuff, but I just don't have time to like discuss today. And we there are a lot of more questions, I mean, which is to be addressed in future, and we can also discuss that. And this is a question I like discussed before. I want to just understand the page transition. I mean, from an algebraic perspective, I want to give it an explicit model. Thank you for listening.
Questions? I do have one question.
Yes.
Can you say a few words about the trumpet?
Yes.
Just a few words, like high level. You don't even need to.
Yeah. Now, yeah. You can just calculate. I was just calculating the trumpet amplitudes for these double square SYK models, and I find that you can define the chord diagrams on a disk with like defect in the middle. And since you have a defect, your chord can actually wind, and there could be some kind of vacuum bubble chords, I mean, floating in the middle, and this actually accounts for the divergence, I mean, of these like diagrams. If you sum them up, you can proliferate those vacuum those vacuum bubbles in the middle, and they can increase indefinitely. So I mean, they can increase infinitely, and so this makes sometimes, I mean, you will just be summing up the same diagram for an infinite number of times. That's what makes those trumpet divergent. Those trumpet amplitude divergent, and interestingly, by examining the structure of these divergences, you find that they exactly have the same divergence pattern as in the JT gravity. For example, if you just have one kind of chord, it's linear.
So just a quick question. In the standard JT gravity, what we say is that you give me some sort of a Riemann surface with a bunch of boundary circles.
Yes.
And we're gonna do the pair of paths decomposition.
Yes,
right? So the Prabhakti composition, something we calculate, there was these moduli associated with PSL2R, and then there's
yes.
the trumpet, half trumpet part, like the part that sticks out
Yes,
from the geodesic to the boundary, asymptotic boundary.
yes.
Does that picture generalize for, or is the belief that this picture generalizes to the skew deformed JT?
That's a wonderful question. I mean, that is one of the questions I'm trying to consider now, because I mean, in this paper, I just considered the case where I just have a 1/2 trumpet, right? Which is from asymptotic boundary to a geodesic boundary. And I just identified the divergence pattern there. And I believe that, for example, I mean, there actually for the case of just one like type of called the pure gravity case, I have a very nice way to like remove all the vacuum bubbles, and which gives a well regularized like trumpet amplitude, which agrees with some earlier discussions by Okuyama, Kazumi, and some other like authors. But I have to say that in the case where we have like more than one type of chord, I haven't like discovered a very satisfying regulator.
That's a more complicated case.
Yeah, that's extremely complicated, because in that case, I think the main problem is that I could not prove that just by removing all the vacuum bubbles actually defines the positive definite like trace. Yeah, and that's basically the problem. But yeah, but you're right. I mean, this is one of the future works which I plan to work on, and also, I mean, that pair of punts like decomposition story, that is also among the problems I have been considering now. I mean, it's like how do I like define Paul diagrams on like a very complicated surfaces, like arbitrary Riemann surface, and with a lot of like and what the like the modulus correspond to, what the moduli I mean correspond to in this case. Yeah, but I think there is a very like well, maybe like Okuyama, Kazumi has some kind of discussions on this, but I'm not very satisfied with that, because he is not referring to the chord like picture at all, I mean, in those discussions. So I want to give it a geometric mean. Right. Yeah.
Any last questions? Not last time.
Yeah. Oh.
Thank you.
Oh.
Thanks so much.
Yeah. Are you having a meeting? I mean.